code here. My plan here we have 5 class days left, not counting exam days. So my plan here is we're going to do a final chapter. I'm calling this chapter C. Fellas, grab one of these. This will be the last set of topics. There will be no homework quiz from this. There will be no test over this. You'll just see this stuff on the final. We will have some homework assignments from this and some Delta Math assignments, but no quiz, no test. Everybody okay there? If you look at your review packet, this thing is quite hefty, but you complete this and turn it in before the last day of classes. I think that's, for everybody, the 22nd. I think that's an X day. It gets you 5 points of extra credit on your final exam, plus you get to use your review packet on the final exam, which is very nice. So my recommendation for you is to do your own review. Don't AI it, don't Google it, don't copy someone else's. Legit do your own. Look the stuff up that you need to do the problem. Make some notes to yourself about what you need to do the problem. The more thorough you are in what you write down and the more usable it is for you, the better the final exam is going to go. The idea here is we take this from being like a memorization exam and turn it into a preparation exam. That if you do a good job preparing your review packet, the final exam should be no problemo. Do you know what I'm saying? Okay, the final exam is ostensibly going to be the same thing as the review packet, less questions, different numbers, possible repeated questions. So there could be stuff that is identical in there. So again, if you do a good job, like you're all set, ready to go, like I'm Copiesville, just writing this thing in here. If you lose your physical copy between now and the X day, I'll put a digital version up on the OneNote. When the once we get to the X day, after I've collected all the reviews, I'll post the key, my worked out key, so you guys can check things over. In the interim, if you have questions on things or want to talk, feel free to ask questions about things before, after class, during community time, whatever. Happy to take a minute and kind of walk through what's going on. Everybody okay there with the plan to finish up the year? Okay. Your most recent tests are graded and entered. I put everyone in for a doubled high test score. If you want to take if you want to do the retake option instead, we need to probably get that figured out by the middle of next week. So send me an email if that's what you want to do. Let me know what test you want to do the retake on and when you're planning on doing it. And we can get that sorted out and try to get that knocked out so that we're not like trying to cram it in the day before the final exam or something. So you have all the tests that you're going to take have been graded. You have scores for. I already went in and put everybody in for a double high test score. If you want something different, though, if you want to do the retake, send me an email, let me know, and we can make the arrangements for that. Everybody okay there? Okay, last thing I'll say about these, the most recent test, is they looked awfully suspicious in the amount of method that seemed unlike anything that I would have taught you. So it seems like there's a fair bit of Googling AI usage, phone usage, on this most recent test. I'm going to tell you right now, for the final, I'm not handing you a final until you've handed me your cell phone. So really, you got to study, you got to know it. You have to know it in your head, or have to know enough on your review packet to be able to do something. Because I'm not going to give you a final until you've given me a cell phone. Everybody okay? And if you see me again next year, it'll be the same case. Okay, no test until you have a phone. Hand it in. Okay? All right, should we get started on the new stuff? All right, the last topic we're going to be talking about are sequences and series. So we'll spend one day here talking about sequences. We'll do a little homework assignment based on that. We'll do a Delta Math based on sequences, and then we'll do another lesson on series, which are related to sequences anyway. A homework assignment and Delta Math on that, and that's it. Okay, so I have two sections. One about sequences, one about series. So a sequence is simply a type of function, but it's a special type of function. It's a type of function where the domain is the counting numbers, the numbers 1, 2, 3, 4, 5. And the range can be any real number. But the inputs to our sequence can only be counting numbers, positive whole numbers, that's it. You cannot put in 0.5 into a sequence and return a value. You can't put in, 7/8. You can't put in -8. The only inputs for a sequence are positive whole numbers. So some examples of the way we might write a sequence. We might write it as a list of numbers like 5, 10, 15, 20, 25. We might write it as an infinite list like 2, 4, 8, 16, 32. And then I'll have like a ... an ellipsis that means that like this pattern is going to continue on in the same fashion forever. We could write it as a set. So this is the set of things that are of the form 1 over k, where k is a positive whole number. So this set would contain things like 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. And then the last way you could write it again as a set, and here we've just been like super general and just called the terms of our sequence like a sub 1, a sub 2, a sub 3, a sub k. So some vocabulary that is really important with sequences is the input to our sequence is called the term number, and the output of our sequence is called the term. So if I look at this first sequence, the first term is 5. So the input for that sequence, when I plug in a 1, a 5 comes out. The second term is a 10. So for that sequence, when I plug a 2 in, a 10 comes out. Is everybody okay with the vocabulary here that we're talking about? It's still the same idea as a function, right? Where we have inputs and we have outputs. The inputs are the term number. The output is the term. Now, you know how for like a function we write, like I might write like f of 1 is equal to 5. For a sequence, what I'd do is I'd write like a sub 1 is equal to 5. So it's like kind of a similar notation, right? Instead of using that function notation, we're going to use this, what's called a sequence notation. Is everybody okay on the vocabulary and the notation here? Okay, if you get confused later on, speak up, because I know it's new. The next thing we're going to talk about is ways to describe a sequence. So like some adjectives you might use to talk about a sequence. So the first adjective we're going to talk about is going to be based on the number of terms in our sequence. And you essentially can classify sequences two ways. Those that are finitely long that have like 5 terms or 12 terms or 57 terms, but like a finite number of them. And then those sequences that are infinitely long, that have a never-ending supply of terms. So if I look at this first example, this is a finite sequence. There's just 5 numbers listed. That's finite. The second sequence is infinite because it has the ... at the end, that it's going to go on forever. That's an infinite sequence. The third sequence, also infinite because the inputs, the k's, there's infinitely many of them. So this will be an infinite sequence, as would this one, because again, there's the ... Is everybody okay with that? Now, one of the ways that we'll want to write down our sequence, typically we don't want to keep using a list to refer to our sequence. Rather, we'd like some kind of formula to describe it. And there's really 2 different ways you might go to write your formula. You might write something called an explicit formula. In an explicit formula, it's basically a formula based on the term number. So like for this first sequence, our explicit formula would be like 5n. Because when I plug 1 in for n, I get 5. When I plug 2 in, I get 10. When I plug 3 in, I get 15, etc., etc., etc. Is everybody okay with that idea? Where it's just based on the term number. The other way of writing this would be with a recursive formula. Where it's based on the previous term. So if I look at that first sequence, notice that each sequence we're adding 5 to the previous. Like to get to 10, we took 5 and added 5 to it. To get to 15, we took the 10 and added 5 to it. To get to 20, we took the 15 and added 5 to it. So that's an example of a recursive formula. This guy is just like notation for the previous term. Now we'll start doing some more examples of just kind of working with these sequences and continuing on. So the first example says find the first 6 terms and the 100th term for the sequence a sub k, in which a sub k is equal to k squared minus 1. So to compute a sub 1, that's the first term. I'm just plugging 1 into my formula for k, so I get 0. To get the second term, I'm plugging 2 in for k. To get 3, then I'll plug 3 in for k. That gives me 8. I'll plug 4 in for k. That'll give me 15. I'll plug 5 in for k. That'll give me 24. Plug 6 in for k. That'll give me 35. And when I plug 100 in for k to get the 100th term, that'll give me, let's see, that's 4 zeros, so 4 nines, 9,999. Is everybody okay with how I'm coming up with the numbers here? I'm just plugging the term number in for n and evaluating. So I might write that my sequence a sub k is 0, 3, 8, 15, 24, 35, ... Okay. As I mentioned before, another way that we might define a sequence is using a recursive formula. So let's look at an example here. I already talked about what I meant by a recursive formula. So here it asks to write or find the first 6 terms and the 100th term for the sequence. We're told b sub 1 is 3. So b sub 2 is going to be the previous term, which should be b sub 1, and then plus 2. So that's going to be 5. Then b sub 3 is going to be the previous term. That's b sub 2 plus 2. So that's 5 plus 2. So that's 7. B sub 4 would be the previous term. So that's b sub 3 plus 2. So 7 plus 2, that's 9. B sub 5 is going to be the previous term. That's b sub 4 plus 2. So 9 plus 2 is 11. And then b sub 6 is going to be the previous term. That's b sub 5 plus 2. So 11 plus 2 is 13. What's the problem with getting b sub 100? I would have had to calculate all 99 terms prior to that in order to do it. So that's rough, right? Do we actually want to do that? I don't think we do. Does anybody see what it's going to be off the top of their head? What do you notice about the pattern here? 3, 5, 7, 9, 11, 13. Well, they're all odd numbers, right? So if this continues on, if I have 100 odd numbers starting at 3, if I had 100 odd numbers starting at 1, what would be the 100th odd number? Would be 201, right? So if we started at 3, it would be 203, I think. But I wouldn't ask you to actually do something like that with a recursive formula because it's just stinky. What's the advantage of the recursive formula? Well, the advantage is typically they're really easy to write. Like the formula is very simple. It's simple to see it. And if you have a computer, like a computer is very good and very capable of doing things recursively. No problem for the computer, but for a human, it's kind of tough. Okay, so next idea. Another way to classify infinite sequences is based on whether those sequences have a limit or not. Right? We've talked about limits when talking about end behavior. So we say if a sequence has a finite limit, we say that sequence is convergent or it converges. If that sequence's limit does not exist or is infinite, we say that sequence is divergent or it diverges. Everybody's okay with the vocabulary? So let's look at some sequences here and decide whether they converge or diverge. And if they do converge, what is the value they're converging to? What would that limit be? So if I look at A, what I'm really looking for is the limit as n goes to infinity of 1 over n. Does this look familiar? This is just the end behavior for a rational function, right? The end behavior for a rational function is dictated by the degree of the numerator and the degree of the denominator. If I look at 1 over n, what's the degree of the numerator? 0, because there's no variable. And the degree of the denominator is 1, because it's n to the first. If the degree of the numerator is less than the degree of the denominator, then we have a horizontal asymptote at y equals 0. So the limit here will be the same, because I have degree of the numerator is less than the degree of the denominator. So the end behavior should be 0 for 1 over n. So its limit is 1 over n, or it's the limit of 1 over n is 0. Now B's a little bit tougher because you're not given the general form, right? You're not given like the 1 over, see how you have the 1 over n here? You're not given that. So my first order of business is to try to look at that and see what the pattern is to write that formula. So if I look at each fraction, what do you notice about the numerator and denominator for each fraction? They go up 1. What if I compare the numerator to the denominators? The numerator is 1 more than the denominator, right? So I could write it as n plus 1 over n. So when n is 1, I should have 1 plus 1 over 1, 2 over 1. When n is 2, I should have 2 plus 1 over 2, or 3 over 2. And it seems like that fits, right? So what's the degree of the numerator in this rational function? 1. What's the degree of the denominator? 1. When the degree of the numerator is equal to the degree of the denominator, we have a horizontal asymptote at the leading coefficient of the numerator over the leading coefficient of the denominator, which in this case is 1 over 1, or just 1. So again, this converges because the limit is finite and exists. This converges because the limit is finite and exists. Let's look at the sequence for C. So we have 2, 4, 6, 8, 10. What is the pattern here going on each time? What do you notice about these numbers? They're all the even numbers, right? So if I want to write this as a formula, how do I get the even numbers? I just take any number and I multiply it by 2, right? So this could just be 2 to the n, or I'm sorry, 2n, not 2 to the n, just 2n, right? 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, and so on and so forth. Now notice this is not a fraction, right? Not a rational function. What type of function is 2n? Linear, right? What's the graph of like y equals 2x look like? Looks like that. What's this end behavior doing? It's going to infinity. So this would be divergent, since the limit is infinite. Everybody's okay here? So the goal really is to try to think about this like a end behavior for a function, right? Sure. All right. And the last one, they were nice, and they gave us the general form here, so we don't have to come up with our own. But what's going to be happening? What are the terms of this sequence? It just goes -1, +1, -1, +1, -1, +1, -1, +1. When n goes to infinity, am I going to tell what's going on? I can't, can I? It's either going to be -1 or +1, but there's no way to tell. So we would say this limit does not exist because there's no way to tell whether it should be +1 or -1. So again, we'd say this then is divergent. Okay. And below here, I wrote down the rules for end behavior for rational functions. In case you didn't remember, we said it verbally basically, so I didn't, but I wrote it down there. Okay. Let's do some more practice on this. So for part A, limit as n goes to infinity of 3n over n plus 1. Who can tell me what this limit is going to be? Is it going to converge or diverge? Good. This does converge. What value does it converge to? 3 is correct. Leading coefficient of the numerator over leading coefficient of the denominator, because the degrees are both 1 in the numerator and denominator. Any questions on how Lucy did that? I think it was Lucy, right? I heard a mumble from that direction. I thought it was you. All right, let's look at the next one then. All right. Who can tell me what this one is? Is it convergent or divergent? And if it converges, what value does it converge to? What would the limit be? So what you want to do is you want to start by looking at the degree of the numerator over the degree of the denominator, because it's a fraction. What's the degree in the numerator? 2. The degree in the denominator is 3. Since the degree of the numerator is less than the degree of the denominator, the limit here should be 0. That is correct. So we'd say this is convergent. And then the last one, this is the hardest one. What do we think's going on here? What's the degree of the numerator? And the degree of the denominator? 2. So what happens when the degree of the numerator is greater than the degree of the denominator? What did we have to do back with rational functions? What did that give us? That was the slant asymptote situation where we had to do the polynomial division. but that's okay for us. That doesn't actually mean we have to do the polynomial division or figure out the equation for the slant asymptote. We don't care. What a slant asymptote is going to mean is this sequence is divergent. So you don't actually have to figure out whether it's infinity or negative infinity or anything else or what that equation is. You can just stop and say divergent. Done. Is everybody okay there? So you see how this is wrapping around and like connecting back to the things we've already studied, which is really nice, right? If the new problem is really the same as the old problem with different dressing on it, I like that because it means I don't have anything new to deal with. It's just like getting used to some new clothes on the same old problem here. All right. So in these previous examples, I've written the explicit formulas for some of these things, and some of them would have been kind of challenging. I'm going to only ask you to be able to write the explicit formula for two certain kinds of sequences. Those sequences are called arithmetic and geometric sequences. An arithmetic sequence is essentially just a linear function. So the key attribute for an arithmetic sequence is the terms of the sequence all share a common or a constant common difference. So if I look at the terms of the sequence, they're all going up or down by the same amount. That amount they're going up or down by is called the constant common difference. We abbreviate that with the letter D. So recursively, our formula is going to look like this, and explicitly, our formula is going to look like that. I put a 1 there. They didn't because they called the first term A, but I would just write that there. So let's do some examples, and I'll show you guys how to write the explicit or recursive equations for equations for these arithmetic sequences. All right, so let's look at example 1. It says, for each of the following sequences, find the constant common difference, the 10th term, a recursive formula for the nth term, and an explicit formula for the nth term. I'm going to do this one last because I'm going to use my explicit formula to just calculate the 10th term. Go straight there. Is everybody okay with that plan? All right. So I'm told that this is a arithmetic sequence. So I'm looking to see what did I have to add or subtract from -6 to get to -2. I added 4, right? -6 plus 4 is -2. And then to go from -2 to 2, I add 4 again. To go from 2 to 6, I added 4. To go from 6 to 10, I added 4. So part A, my common difference is 4. Everybody feel good there? We'll do C next. So to write our recursive formula, I'm just going to be using this. So I'm just filling the D into that formula that's written above, and then listing what the first term is, because I have to give a starting point if it's based on the previous term. I have to give you the start value for the sequence, and then from that you can generate anything you want. Is everybody okay there? And then to get the explicit formula, I'm using this formula. So the first term in my sequence is -6. And my constant difference is 4. And if I distribute the 4 through and I combine some like terms, I'd get like 4n minus 10. You don't have to do that, but it makes doing part B a little bit simpler. So if I want a sub 10, I'm just going to do 4 times 10 minus 10. So that's 30. Now you could have generated the 10th term iteratively just by adding 4 until you got 10 numbers written down, which is fine. You can do it that way also. But if that was the 100th term they asked for, boy, howdy, I don't want to do that, right? Even with my calculator, that's an obnoxious question to kind of keep track of what number am I on. Yuckarooskies. I'm going to skip doing example 2 here because I don't like the logs in there. It's more difficult than I want it to be, so I'm just going to skip that example. Definitely harder than anything I would ask you to do. Now, the second type of sequence I would ask you to write the explicit formula for is a geometric sequence. A geometric sequence is essentially just an exponential function because each term is or I should say the quotient of consecutive terms is constant. We call that a constant common ratio. So basically it means that I'm multiplying each term by a number to get the next term. And it's the same number each time. So again, my explicit formula is going to look like this. So a sub 1, the first term, times r, that's our constant common ratio, to the n minus 1, or our explicit formula, or recursive formula is the previous term times r. So again, I'm going to skip that second example. It says for each of the following geometric sequences, find the common ratio, the 10th term, the recursive rule, and the explicit rule. Again, I'm going to do it in the same order I did last time and find that 10th term as the final, because I'll just use the explicit formula to do it. So I'm going to look what times 3 gives me 6. 2. And 2 times 6 also gives me 12. And 2 times 12 gives me 24. And 24 times 2 gives me 48. So I know that that common ratio is just 2. My recursive formula then is going to be the previous term times 2, provided the first term is 3. So again, I'm just using that formula here, plugging in my r and my first term. So there's my previous term. Everybody's okay there? Or my explicit formula. So I just plugged in the first term in R. There's nothing to simplify. It's done. That's nice. So now I'll circle back and do B. So that's going to be 3 times 2 to the 10 minus 1. So 2 to the 9th is 512. So when I multiply that by 3, that's 1536. And again, you could just type that in your calculator if you wanted to. I did it in my head, but so far so good. Basically pretty easy, right? We're just basically plugging stuff into a formula. The most challenging type of question in our last example here is one like this. It says the second and fifth terms of a sequence are 3 and 24 respectively. Find the explicit formula for the sequence if it is arithmetic or if it's geometric. Yes. You're going to miss the calculator part, though. Okay. So we're told this, right? The second term is 3, and the fifth term is 24. And what we want is that formula, right? Now, I could do this a couple of different ways, but I'm going to use my calculator and make this as easy on myself as possible. Everybody good with that plan? If you have your graphing calculator with you, I ask you to take it out now so you can follow along. I do have one extra up here on my desk if you want to borrow it to look at. So the general idea of what we're going to do here, you're welcome, is we're going to take these two sequences, or two terms from our sequence, and think about them as an XY table, where the term number is our X, and the term value is our Y. And we're going to enter that list into our calculator and do a linear regression on it. So if you remember that back from chapter 12, to enter the list into our calculator, we're going to press Stat, and then Edit. And into L1, I'm going to type my X's. And into L2, I'm going to type my Y's. Or I could say, think about it as my term numbers into L1 and my term values into L2. Those of you following along, are we okay to here? Okay. I'm going to exit out of here, so second and the mode button, that exits out. And then I'm going to go back to the stat menu. This time I'm going to go over to the Calc tab, scroll down to Command 4 where it says linreg AX plus B. Press Enter, make sure that the X list is L1, the Y list is L2, and then just hit Calculate. So what this tells me is that my equation should be A sub n equals 7n minus 11. Boom, done. How do you like that? Alternatively, what you would do is you'd be like plugging in the n and the a sub n. So like you plug in 3 for a sub n and 2 for n. And then also plug in 24 for a sub n and 5 for n. And then you'd have a system of equations to solve. Yuck, let's not. The calculator will do it for us in like 2 seconds. No problemo. I'll do that. We've already covered how to do that. The second, or for part B, we're going to do this the exact same way. But this time, instead of doing a ln reg, this type of equation is exponential, so I'm just going to do an exponential regression on it. So again, just go back to the stat, over to the calc tab, scroll down to command 0, exp reg, press enter, make sure again my x list is L1 and my y list is L2, and then just hit calculate. So my answer should be a sub n equals 0.75 times 2 to the x. Or I should say 2 to the n. And that'll do it. Absolutely. What do you guys think? No problemo. So for homework set number 1, we're gonna use these questions from the that I've posted into OneNote. So let's just do like 1 through 31 odd, right? That sounds pretty good. That's like 15 questions or something. And I think next class we'll work on I have a Delta Math assignment based on these topics that we can work on. The following class we'll talk about series, same kind of thing. That following class we'll have a Delta Math assignment based on those series. Those are our last homeworks. They're going to be these 2 sets of homework problems and these 2 Delta Maths. But while all this is going on, what else should you be working on? Your review. Don't wait till last minute to do it. Start so you can do a thorough job on the questions. When you start getting tired, take a break, because it doesn't have to be done for like, what do we got? Like almost 2 weeks, I think, till this thing is due. So you don't have to rush through it, but start early so you can take your time and be thorough, right? Try to do a little bit every night. When you get to stuck or you're not sure, you can skip and circle back on stuff. But, start early so you can take your time and be thorough and not make any silly mistakes on it. Since you get to use it on your exam, you want to be really thorough and point out like all the little work that you need to do and all the steps and how you know what to do so that it's useful to you on your final exam, right? But that's it for me for today. Everybody feel good? Absolutely. All right. Fair enough.